Significant figures is a topic that many students struggle with when they begin learning chemistry. But what are significant figures and why are they important? Significant figures are the number of digits in a measurement that we can say we know with some degree of confidence. Significant figures are all about one thing, and that is precision. Let's start with a common measurement everyone has heard of before and try to determine how many significant figures the measurement may have. According to the World Population Clock at the time of this video, the population of the Earth is 7,581,395,634 people. But how precise is this measurement really? Well, the first digit, the 7, we can say with a great degree of confidence is correct, that there are 7 billion people on the Earth at least. What about the digit to the right of the 7, the 5? How confident are we that this 5 is correct? Maybe we are pretty sure that this digit is precise. We can continue this through each digit of the number and until we reach our last digit, the 4. This last digit is constantly changing as people are born and as people die, so we can't really say with any degree of confidence that this digit is precise. How does this all relate to significant figures then? Well, if we are only confident in the first two digits of our population measurement, then we shouldn't really say that the population of the Earth is 7,581,395,634, because all the digits after the first two digits are meaningless in the sense we aren't confident they are precise. So really, what we should say is that the population of the Earth is 7,500,000,000. Or we can write it in scientific notation as 7.5 times 10 raised to the power 9. Accounting for significant figures in the population of Earth means we are confident in our measurement. Let's look at another example involving a meter stick. We can see that a meter stick is a meter long and there's markings for centimeters along the side. Let's say we want to measure someone's height with the meter stick. We measure this person and their height is 1.90 meters. There's a lot of information actually in this measurement. For one, we know that this person is also 190 centimeters. However, we could also say that they are 0.00190 kilometers. The important thing here is that there are three significant figures in this measurement. Because we measured to the nearest centimeter, we know the precision of our measurement is down to the nearest centimeter. What we can't say is that this person's height is 1.900 meters or 190.0 centimeters, or adding another 0 at the end of the kilometers measurement. This trailing 0 would indicate that you measured to the closest millimeter, which we did not. It is very important to analyze each digit in a measurement and whether we can say with confidence that the digit we are looking at is precise. We can always add leading zeros or zeros after the decimal point but before the measurement, converting between units like the leading zeros in our kilometers measurement. What we can't do is say that this person is 1900 millimeters tall, because we didn't measure millimeters. This person could be anywhere from 1900 to 1909 millimeters, but we just don't know. To wrap this example up, try to understand why only 3 of the digits are significant and why only those digits have any meaning. We will work through more examples to solidify this idea of precision and significant figures. Scientific notation is a way of writing either very large or very small numbers that may be too large or too small to write conveniently in the standard decimal form we usually use. Numbers in scientific notation are expressed in the form x times 10 to the y. X is known as the coefficient and 10 to the y is your base. For example, let's look at the United States national debt. According to $500 billion. This is a very large number to write down, but we can express this number more succinctly using scientific notation. For large numbers, we want to imagine that there is a decimal point at the end of the last digit, like so. To find the value of y in our form x times 10 to the power y, we want to count how many places our decimal moves to reach the right side of our first digit, like so. I count 13 digits following the 2, so our y equals 13 in the form x times 10 to the power y. To find the x, we simply stop or cut off the trailing zeros, so our final form in scientific notation of the U.S. national debt is 2.05 times 10 raised to the power 13. To move back to decimal form, we simply move the decimal point 13 digits to the right and add zeros in the empty digit spots we are going back to. Now we put the zeros in. And you can see, once we get rid of the decimal, that this is our original number, 20 trillion and 500 billion. Let's look at another example this time for something very, very small. The diameter of an atom. An atom can range from 0.1 to 0.5 nanometers. This would be 0.00000000001 meters. If you had to consistently write this value down, it might be tedious to write all those zeros over and over again. Let's express this in scientific notation. To express this number in scientific notation, we move the decimal point to the right until we reach the right side of our last digit, and we count the digits along the way. We move 10 digits, then we simply drop the leading zeros and express this in the form 1 times 10 to the negative 10. Note how the y value is negative. Just remember that numbers smaller than 1 in scientific notation have a negative exponent, and numbers larger than 1 in scientific notation have positive exponents. To get back to decimal form, we simply move the decimal 10 digits to the left to get back to our original value of 0.00000000001. In later videos, we'll see how scientific notation and significant figures go hand in hand together.